Hey guys, welcome to this video. This week here are some basic photo filters we could get from any editing applet. And these are some common examples of applying three filters on the original photo: sharpness, contrast, and blurring. But what is Fourier transform? I guess not too many people know this if you are not math student. And how to link these two seemingly unrelated things is a more difficult question to be answered. So let's keep the second question and start first one. If you try to search it on Google, you will get so many complex functions. But I don't want to introduce Fourier transform from this. This week here, I will use a certain animated approach to thinking about this super important idea, Fourier transform in math. The central example to start is going to be the classic one. Now, let's dive in. They look very familiar, right? These are some basic trigonometry function waves: sine t, cosine t, cosine 2t. Then, how about this wave? This wave can be expressed as the combination of sine t, cosine t, and cosine 2t. Now, let's express this wave as a function on the time domain. So the wave on the plane coordinate system. But if we decompose the wave like this, on this condition, we can use three-dimensional coordinate system. Then we call the new axis frequency domain. So on the three-dimensional coordinate system, the wave can be decomposed into three basic trigonometry function waves. Pretty interesting, right? Either of those waves really mix them all together. Feels akin to unmixing three paint colors that's all being stirred up together. Now we extract the frequency domain and the axis. Here, the amplitude of each wave can be expressed as these three values. And then we back to the previous diagram. The start points of each wave are different. We call them phase, and phase is this axis. Since each wave has their own value of phase, so we need to draw three arrows as phases of three waves. Then we can see this way is the Fourier transform, and the inverse way is the inverse Fourier transform. Now, we almost know what is Fourier transform look like. And the attentive viewers among you might notice this is more about transformation on waves. So you might have another question. What is the connection between waves and photo filters? Now it's time to introduce digital image. Depending on whether the image resolution is fixed, it may be of vector or raster type. In this video, we only talk about raster image, so the digital image in this video always means the raster image. Raster image is defined as technically characterized by the width and height of the image in pixels, and by the number of bits per pixel. This definition is quite hard to understand, right? So, we can describe the raster image in a more familiar way. Raster image can be described in three different types. They are GIF, JPEG, PNG. Here are some corresponding images to help you better understand and distinguish these three different image types. As we can see, the GIF is a moving image. By comparing JPEG and PNG image, we could find PNG image is sharper than JPEG. This because JPEG image are lossy compressed during storage, while PNG performs lossless compression. So it is very clear to see the quality between these two images. As we already defined before, a digital image is normally consists of an array of pixels, like this image. And if we zoom in this image, each pixel is a set of value red, green, blue. And each red, green, blue channel, we call them RGB channel, contains a set of intensity or grayscale value, like the right column image. In the space of an image, the intensity value at each location or position could define a unique image. Like this graph, the left original image could be defined by RGB channel and the intensity or grayscale. For example, if we analyze this digital image, we could get the histogram like this. Hence, the digital image could be expressed as image waves in the spatial domain. Therefore, we can find some connection between digital image and the Fourier transform. And then, if we have a single row or column of pixel from any image, then we can get the wave of this pixel by using FFTW. And FFTW is a C subroutine library for computing the discrete Fourier transform in one or more dimensionals. Then, if we adding these regular waves together, we can get a complex waves, which is close to the wave of the single pixel. As we already know, the digital image is normally consists of an array of pixels. So, if we get the wave of single pixel, it is possible to get the wave of the original image pattern. And if you can continue in this manner, adding more waves and adjusting them, the result will get closer and closer to the actual original image pattern. Eventually, exactly original profile of this image can be produced by adding enough waves. So until now, you may think, yes, I know how the Fourier transform work on the image wave. But if you focus on the detail of FFTW, this software, you can see this is not based on the Fourier transform. FFTW works for compute discrete Fourier transform. So now, many of you guys may be curious, what is discrete Fourier transform? So by comparing the graph and the definition of Fourier transform and discrete Fourier transform, we could find the discrete Fourier transform is discrete and finite in the time and frequency. This is quite different with the Fourier transform, since Fourier transform is continuous in time and frequency. But the discrete input and output value in discrete Fourier transform make computer manipulation convenient. And when we working with the Fourier transform on the computer, usually involves the discrete Fourier transform. So this means the discrete Fourier transform used to perform Fourier analysis in many particle applications. After that, I really want to show a glimpse of how the Fourier transform idea extends well beyond the imagined waves. If you're watching until now, it's time to talk about how to apply Fourier transform on the photo filters. And in this step, we will use another software, Imagine Magic. But in this video, I will not talk about how the Imagine Magic and the FFTW library work, since this is more about computer science. But based on the coding of this, we can get the photo filters. The general strategy is gonna be to build for ourselves a mathematical machine that transfers an image into waves, then decompose this wave into several pure waves. And through changing the amplitude, the period, and the phase of these waves, we can produce several new waves. Then we can use inverse Fourier analysis to compose them into a new image with filter. If you are wondering the specific solution, please have a look at the link below this video. When I'm doing the research about the Fourier transform, I found something really interesting and crazy. The article said the most popular method of analyzing brain signals is to decompose it into its components by using the Fourier transform. So if you are interested about this, please have a look at the link below this video. Thank you very much for watching this video. If you have free time, please complete the survey below this video. It's quite important for my final project. And if you are interested with this topic or you have some advice about this video, it's very welcome to contact me or comment below this video. Thanks again for watching this video.